Hello, students. We're going to talk about the self-ionization of water and pH. So this should be review, but I'll go back through it. So if you have water molecules in pure water, one water molecule will act as an acid or proton donor, and the other one will act as a base, proton acceptor. So I'll show it here. The H plus will donate to the base. And what you'll end up with then is hydroxide and hydronium ion that's formed. This is an equilibrium scenario. And the equilibrium expression that we could write would be K equals H3O plus times hydroxide over the water. But the water, if you recall from our previous discussions, we talked about how pure liquids and solids do not appear in the equilibrium expression. The next slide kind of goes through a little bit more detail on that. This will equal what's called Kw, which is a very small value of 1.0 times 10 to the negative 14. So the equilibrium constant for this process is very, very tiny. Okay, now here's a little bit more detail, and maybe a little bit more than you need, but here's the K expression. It's showing it as a Ka initially because water is acting as an acid, and it's looking at it from that perspective. And then the water part, the concentration of the water, is substituted with this very large number of 55 molar. You won't need to know this part, but I just want you to know where that comes from. I mentioned it in the previous PowerPoint that the concentrations of solids and liquids is really large and ends up being like a constant. So where does that 55 come from? If I take 1 liter of water and I know its density, which is 1 gram per mil, we could do some calculating and convert that to molarity. And what we'd end up is with 55 molar. I won't go through the calculation because I'm not going to, you don't need to know it. But I just want you to see then that that concentration is absorbed into the K. And we now have this new K, which is called Kw. And so the important part here is just this part of the Kw expression, which is the same as this one. This one's flipped. Okay, now if we know that value at standard value of 1.0 times 10 to the negative 14, then if I take the square root of this number, I know what the concentrations are of H plus and hydronium. I'm sorry, and hydroxide. Those guys are equal. And they equal 1.0 times 10 to the negative 7 molar. Okay, that's not the easiest number to deal with, for me to constantly say 1.0 times 10 to the negative 7. And so instead what was done is it was converted to pH, which is 7.00. And this is a math manipulation. So this math manipulation should remind you of the one we talked about with Ka and pKa. So it's just much easier to reference pH as 7 than it is to say that the H plus is 1.0 times 10 to the negative 7. Just one quick thing. We don't do math in this class, but just so you know that the typical pHs have 2 decimal places, and that has to do with some sig fig rules from the concentration having 2 sig figs. All right, the hydroxide ion concentration can be expressed as POH, which for this would end up being 7. And if you notice something, pH plus POH, notice what number it adds up to. It adds up to 14. And that's because we could take the pKw, which is just taking the negative log of the kW, and we would get 14. So it's good to know then that there's this relationship between hydroxide and hydronium ion. Okay, so now let's think about this. I'm going to put our expression up here for Kw. Okay, so neutral, hydronium, and hydroxide equal each other. Okay, but when we have, and let's start with the acidic one. When we have an acid in solution, we see an increase in H3O+, because that's what acids do. They form hydronium. Okay, so now let's think about this. If we increase H3O+, we have to maintain the same constant. So what does that mean for hydroxide? Is for sure hydroxide's going to decrease. Okay, so we'll see a decrease in hydroxide. Okay, acidic solutions then, if we increase H3O+, what does that do with taking the negative log of that? Well, what it's going to do is we're going to see a decrease in the value of pH. So making H3O+ bigger will decrease the pH because of the negative log expression there. Okay, so in an acidic solution, the pH goes down. In the hydroxide, concentration goes down, but the POH goes up. And then remember, those will always add up to 14. Okay, so that's in an acidic solution. In a basic solution, we see an increase in hydroxide because that's what bases form, OH minus. Okay, that means we would see a decrease in POH. Okay, and then the other one is reverse of that, right? Increase in hydroxide decreases H3O+, and that increases the pH. And so with this, our starting point was pH 7, that was neutral. Basic solutions, though, increase the pH from that. So those are greater than 7. And acidic solutions decrease the pH from 7. Okay, so here's a scale that you've probably seen before of very acidic solutions, very basic. So our acidic ones are like hydrochloric acid, gastric juices, vinegar, tomato juice. So as I'm sure you've seen this graphic before. For biochemistry, it turns out that really we have a very narrow range that is important for us. Oh, I keep doing that. Sorry. I just wanted to do the highlighter. So the important range is the pH of most body fluids is between 6.5 and 8.0. And that's what we think of as physiological pH. Later, when we start talking a lot about the pH of the bloodstream, we tend to focus on pH 7.4. And so this is going to be something that you should know, and that is going to be important in our discussions. So in the biochemistry that we explore, we're not really concerned with super acidic ranges or very basic, because those wouldn't exist in the body in the reactions that we're looking at.